don't know how the screen protector got hole.
I didn't
Got one time my iPhone also got one time one hole. How the hell the screen protector got one hole?
Oh shit, later I show you. Got crack already. Got crack on the side.
On the screen.
Yeah, the screen of the Gorilla Plus as well. How Gorilla?
Yeah.
Okay, so I think we'll make a start. So, welcome to the tutorial on advanced computer architectures. My name is Stephen Turner. If you want to send me an email, if you have any questions about the course, you can send me an email to this address, steve@email.ntu.edu.sg. If you want to come and talk to me in person, my office is in the Computer Engineering Building, 104-2A-14, or you can phone me on my office phone.
Maybe he did.
Okay, so can I ask you just to put your initial by the attendance sheet, please?
What? Oh, big class ah?
Class.
No more place to see already. Watching you.
You waiting for me to come? Fun
Got so many people on.
Okay, so for those people who have come in late, I was just introducing myself. My name is Stephen Turner, and you can contact me either by email or my office.
Private mail ah? Yeah lah. Where do you sit?
No space lah.
Okay.
Sit on the floor lah. Huh? Yeah, sit on the floor.
Why he likes to make
Seriously, all in this class ah? Yeah, got the
likes to make his cheek. He likes to jump his cheek.
Yeah, you can see right. It's a heavy day. This one is a heavy thing.
I like to.
Okay, so this morning's tutorial is about performance and cost. So we have 4 questions in this week's tutorial.
You have to pay attention. Just trying to impress your dad or that.
Walao eh.
I think this one is a picture one.
Yeah lah, take
Okay,
picture
so
later.
the first question is about how to calculate MIPS and megaflops ratings. So MIPS is million of instructions per second and includes all instructions. Megaflops includes the floating point instructions. And we're told that we have a program, and this program has a mix of instructions. So in the program, 10% of the instructions are floating point multiply, 15% floating point add, 5% floating point divide, and 70% integer instructions. And we're told we have 2 machines. The first machine has built-in floating point for executing the floating point instructions, and this machine requires a certain number of clock cycles for the different instructions. So for floating point multiply, 6 clock cycles, floating point add 4, floating point divide 20, and an integer takes 2 clock cycles. The other machine, NFP, has no floating point unit. So for this machine, we have to emulate the floating point instructions using integer instructions. So the integer instructions take 2 clock cycles, and we're told we need 30 integer instructions for floating point multiply, 20 for floating point add, 50 for floating point divide, and we have to emulate those floating point operations using integer instructions. And finally, we're told both machines have a clock rate of 1 gigahertz. And we're asked to find the MIPS and the megaflops ratings for both machines. Okay, so I'm using two projectors, okay, so I'm going to keep some information on the main projector and display the solutions on the other displays. Okay, so we're given some, in the lectures you were given some equations which tell you how to calculate the MIPS and the megaflops. So the MIPS is defined by the number of instructions per second. So to calculate the MIPS, you can take the total number of instructions and you can divide it by the execution time. But then you want it in terms of million instructions per second, so you also divide by 10 to the 6. For megaflops, you do the same, except that you just use the floating point instructions rather than all of the instructions. The execution time we can calculate in different ways. So we can calculate the execution time as the number of clock cycles times the cycle time, which is the time per cycle, or alternatively, we can consider the execution time as the number of clock cycles divided by the clock rate. Okay. Okay, I think I'll switch to projectors. So I'll use this main. I'll use this main projector for the answer, and some of the other details are around the side. Then you can look. Then you're all looking at the front. Okay, so we have enough equations to be able to solve this. So let's see how we can solve it. Before I do that, though, I'd like to ask you how many of you have solved it. So for the first machine that has floating point built into the machine, what is the MIPS rate? Can anybody tell me? Anybody calculated a value? Somebody give me an answer. What have you done? What have you calculated? Nobody tried this? Somebody must have had a go. What have you got? What answer have you got? Or can anybody work it out now in a few minutes?
Simplify it a bit.
What he said, he asked us to find out.
Okay, let's see how we can work it out then. So we're going to use these equations. So we want to know the number of instructions, and we want to really work out the execution time. And we're not told how many instructions there are, but it doesn't really matter. Let's just assume that the number of instructions is A. Okay, because we're going to cancel A out later anyway, so it doesn't actually matter what it is. So let's assume the number of instructions is A. And then for for the machine with floating point arithmetic, we can calculate the execution time by calculating the clock cycles and then multiplying by the cycle time. Okay, so if you look at the question, we're told what the we're told the mix of instructions in the program, and we're told what the clock cycles per instruction are. So we can use that information. Okay, so we're told that there are, what, 10% floating point multiply, and the number of clock cycles for floating point multiply is 6, 15% floating point add, and the number of clock cycles for floating point add is 4, 5% floating point divide, and the number of clock cycles for divide 20, 70% integer, 2 clock cycles. Okay, and we're told the machine is 1 gigahertz, so the cycle time will be 1 nanosecond. Okay, so that's the execution time by taking the proportion of instructions of each type that have executed and multiplying it by the different clock cycle times. Okay, and then you can do some simple arithmetic, and you find that the execution time is the number of instructions A times 3.6 by calculating these percentages and adding them up and so on. Okay, so we have the execution time, A times 3.6 nanoseconds. And from the execution time then, we can get the MIPS by dividing the number of instructions by the execution time. So the number of instructions was A, this is the execution time, the A's cancel out, so the MIPS rating is 1 divided by 3.6. We have nanoseconds here, which is 10 to the minus 9, but we multiply by 10 to the 6, so we get 10 to the minus 3, and then when we do the division, we get 277.8. Okay? So you just use the basic equations and do the arithmetic. Any questions so far?
Nanosecond.
Okay, so you know how to calculate the bits now.
Nano, micro, milli, micro, nano, 9.
Megaflops is similar, except that instead of using the total instructions, we just take into account the floating point instructions that are executed. So again, from the question, it says that there are 10% floating point instructions, 15% floating point add, 5% floating point divide. So the number of floating point instructions executed is actually A times 10% plus 15% plus 5%. Again, we divide that by the execution time. The execution time is the same, okay? But the number of instructions is different. So 10% plus 15% plus 5% comes to 0.3. So now the megaflops rating is 0.3. Again, the A's cancel out. It's 0.3 times 3.6 times 10 to the minus 3. Because again, this is in nanoseconds, we have 10 to the 6. So that comes to 83.3. Okay, so a similar way of working it out, but you only include the floating point operations. Any questions? Sorry? Speak a bit louder.
The second, to calculate the makeup taking on operations.
Yes.
And just multiply 2 times 5. Because I know the percentile of the floating point is 100, so I just multiply.
Okay, yeah, you could do it that way if you like. Yes, I mean, it would come out to the same answer. Yes, because you know that 30% of the instructions are floating point instructions. So, yeah, I mean, it's going to give you the same answer. For a few of these questions, there are some alternative ways of working out the answer. So what I show you is not necessarily the only way. You can sometimes work it out in a slightly different way. Okay, any other questions? Okay, so let's go on to the machine without the floating point arithmetic. So here we have to emulate the floating point instruction by using integer instructions. So again, from the question, we know that there are 10% floating point multiply, and the floating point multiply takes 30 integer instructions. There are 15% floating point add, and a floating point add takes 20 integer instructions, and there are 5% floating point divide, and the floating point divide takes 50 integer instructions. Each integer instructions is 2 clock cycles, and there are 70% integer instructions in the program, again taking 2 clock cycles. So again, the calculation is similar but slightly different. We take the percentage of each instruction, multiply it by the number of integer instructions required, and then multiply by 2. Okay, so again, we can work out the arithmetic, and if you work out the arithmetic, you find that this comes to 3 plus 3 plus 2.5 times 2 plus 1.4, which is 18.4. So the execution time is the number of instructions, A, times 18.4 nanoseconds. Okay, so far? Now, I'd like to ask you a question. In order to calculate the MIPS and the megaflops, we need to know the number of instructions. Do we use the original number of instructions in the program, or do we use the actual number of instructions executed, including emulation? Sorry? Okay. I'll show you the calculation both ways. But the question actually talks about native instructions. So that should really include the instructions for emulation. But I'll show you the calculation both ways, and then you know how to do it whichever way you asked. Okay, so if we use the original number of instructions, the calculation is similar to before. The MIPS has a number of instructions A, we have the new execution time, so we cancel out the A's, we get 1 over 18.4 times 10 to the minus 3, which is 54.3. If we do it using the number of instructions including emulation, then we have to calculate how many instructions we actually execute. So again, we can go back to the 10%, 15%, 5%, 70%. A floating point multiply actually executes 30 instructions. A floating point add executes 20 instructions. A floating point divide executes 50 instructions. So, in fact, the number of integer instructions actually executed is A times 9.2, and we divide that by A times 18.4, so we get 1 over 2 times 10 to the minus 3, which is 500. And if you think about it, that's a logical answer, because the clock rate is 1 gigahertz, and each instruction takes 2 clock cycles, so the number of instructions per second is going to be half the number of clock cycles per second. And again, for megaflops, we can do it 2 ways. If we use the original number of instructions and see how many floating point instructions there are, then again, as for the previous machine, we have 10% floating point multiply, 15% floating point add, 5% floating point divide, divided by the execution time. Which again is 0.3 divided by the execution time, which is 16.3. But if you're talking about the actual number of instructions executed, then this machine doesn't have any floating point unit, so therefore technically it's not executing any floating point instructions. So in terms of the actual number of instructions, it's really 0, because the machine is just executing integer instructions. Okay, so you can, there are 2 solutions really, depending upon the assumptions you make, and the question should really make it clear. And in this case, the question asked for the native MIPS and the native megaflops. So really, you should use the actual values. Okay, so that's question number 1. Are you all happy with that? Any questions on question number 1? Okay, let's move on.
No, but down here I think he played out then he can cancel, that's what they don't want. But I haven't, because his denominator he also can evaluate to this, so somehow along the way he cancel. I haven't calculated the full sequence yet.
Okay, so for question number 2, again we're given some information.
He cancelled out.
So we have 2 programs and 2 machines.
Yeah, to do out the whole thing first.
So program P1 takes 10 seconds on machine M1 and 5 seconds on machine M2. Program P2 takes 3 seconds on machine M1 and 4 seconds on M2. We're told the number of instructions. P1 requires
Have to
200 times
calculate
10 to the 6
out.
instructions on M1
I haven't
and 160 times 10 to the 6 instructions on M2. We're told the clock rates, M1 has a clock rate of 200 megahertz and M2 a clock rate of 300 megahertz. So this question is about CPI, or clock cycles per instruction. So again, there are some basic relations we can use. The clock cycles per instruction is the number of clock cycles executed divided by the number of instructions executed. Okay, that gives you the average clock cycles per instruction. Or you can calculate it in a slightly different way by taking the cycles per second and dividing by the instructions per second. Okay, so both of them will give you the same result. In some cases it's more convenient to use the second way, in some cases it's more convenient to use the first way. Okay, so again I'll leave the information on the displays around the edge, and part A of the question, we're told that we want to find this clock cycle per instruction, or CPI, for program P1 on machines M1 and M2. Okay, so in this case we're going to use CPI as cycles per second over instructions per second. So let's do it for machine M1 first, and we can calculate the instructions per second because we know the total number of instructions taken by P1. Okay, P1 we're told takes requires 200 times 10 to the 6 instructions, and it takes 10 seconds to execute. So the instructions per second is 20 times 10 to the 6. So from that we can calculate the CPI because we know the cycles per second. The cycles per second is just the clock rate, okay, and machine M1, we're told, has a clock rate of 200 megahertz. So the cycles per second is 200 times 10 to the 6. The cycles per second is 200 times 10 to the 6. The instructions per second is 200 times 10 to the 6 divided by 10, which is 20 times 10 to the 6. So the CPI is 10. Okay, any questions so far? Has anybody solved this? Can you tell me what the CPI for M2 is? Okay, 9.375, yes. So how do we get that? So for M2, again, the instructions per second is the total number of instructions, which is 160 times 10 to the 6, we're told. And we're told that it takes 5 seconds to execute, so the instructions per second is 32 times 10 to the 6. And then again, for the CPI, we take the cycles per second, which is the clock rate. So for M2, that's 300 megahertz. Divide it by the instructions per second, which is 32 times 10 to the 6, and we get 9.375. Okay, good. Any questions on that? Okay, let's go on. So, for section B of the question, we're told that we can assume that the CPI for program 2 is the same as the CPI for program 1, P1, on each of the two machines. And we're asked to find the number of instructions for P2 on each machine. So again, from the relationship I told you before, the CPI is the number of clock cycles divided by the total number of instructions. So you can rearrange that and say the total number of instructions is the number of clock cycles divided by the CPI. Okay? So we can also work out the number of clock cycles. The number of clock cycles is the cycles per second, or the total number of clock cycles is the cycles per second times the execution time. Okay, so again, we're sort of using these basic relationships, and we have enough information to be able to solve the problem. Has anybody done this? Can you tell me what the number of instructions is for M1? Okay, so let's see how we can do this. So we have program P2 on M1. So we can simply plug into this equation. Okay, so the number of instructions is the number of clock cycles divided by the CPI. And the number of clock cycles is the cycles per second times the execution time. For machine M1, the number of clock cycles per second is 200 times 10 to the 6, the clock rate. And we're told that P2 takes 3 seconds on M1. So the number of clock cycles is 200 times 10 to the 6 times 3. And then we're told that the CPI for P2 is the same as the CPI for P1. And if you remember from part A of the question, we calculated that the CPI is 10, okay, for machine M1. So we take 200 times 10 to the 6 times 3, divide by 10, and get the answer as the number of instructions 60 times 10 to the 6. Okay, so again, just putting the values into the equations that we have. Any questions? What about M2? Anybody tell me what it would be for M2?
Sorry.
3 second.
Yeah, that 3
Sorry?
seconds. Then the CPI this one.
100.
This one is 10 because it says
Okay,
both the CPI
128.
for program 2. Yeah.
So again, we can do it the same way.
3 second.
Program 2.
The number of clock cycles is the cycles per second times the execution time. We're told for machine M2 that the clock rate is 300 megahertz. So the number of clock cycles, number of cycles per second is 300 times 10 to the 6. And we're told that P2 takes 4 seconds on machine M2. So this is the total number of clock cycles, 300 times 10 to the 6 times 4. And then we divide by the CPI. And from the previous question or previous section, we worked out the CPI was 9.375. So we simply do the arithmetic, 1200 times 10 to the 6 divided by 9.375, which is 128 times 10 to the 6. Okay, any questions? Okay, let's move on. So, section C of this question is about performance and cost effectiveness. Okay, so we're told that machine M1 costs 10,000 and machine M2 costs 15,000. We have a rather unusual way of calculating performance because we're told that P1 must be executed 200 times each hour, and then the performance is measured by how many times per hour we can execute P2. Okay, that's rather a strange way of measuring performance, but that's what the question tells us, so that's what we have to do. So, to calculate the performance then, we know P1 must be executed 200 times each hour, so we can see how much time we have left to execute P2. Okay, so on machine M1, one hour is 3,600 seconds. P1 has to be executed 200 times an hour, and we're told that P1 takes 10 seconds on M1. Okay, so in an hour we have 3,600 seconds. P1 will take 2,000 of those seconds. So we have 1,600 seconds left. And we're told that P2 takes 3 seconds on machine M1. So the number of times we can execute P2 per hour is going to be 1,600 divided by 3, which is 533.333. Okay? So we can treat this, or the question tells us we can regard this as a measure of performance in terms of the number of times per hour P2 can be executed. And we can calculate cost effectiveness as performance divided by cost. So the performance is 533.333, the cost is $10,000, so a measure of the cost effectiveness is 0.053. And then we can do the same for M2. So again, on machine M2, program P1 takes 5 seconds, and we have 3,600 seconds in an hour. So program P1 will take 200 times 5, or 1,000 seconds, which leaves us with 2,600 seconds left. And P2 takes time 4 seconds on M2, so we divide by 4 to get the number of times we can execute P2 per hour. Okay, so we can execute P2 more times per hour than on a machine M2 than on machine M1.
6.0
But if we work out the cost effectiveness, then again the cost effectiveness is the performance divided by the cost, which in this case is 0.043. So we can compare the performance and the cost effectiveness. M2 has a better performance by a factor of 650 divided by 533. But because M2 is more expensive, M1 is actually more cost effective. When we divide the performance by the cost and then take the ratio, M2 is more cost effective than M1 is more cost effective than M2 by a factor of 1.233. Okay, any questions?
The 3600 is what?
Okay, let's move on then to question number 3.
60 times 60.
So question number 3, we're told that we have an instruction set with 4 classes of instructions, A, B, C, and D, and we're told that we have 2 machines. Machine M1 has a clock rate of 500 megahertz, and the number of cycles per instruction for these 4 classes is 1 for A, 2 for B, 3 for C, 4 for D. M2 has a clock rate of 750 megahertz, and the number of cycles per instruction is 2 for class A, 2 for class B, 4 for class C, 4 for class D. We're asked to find the peak performance of M1 and M2. So in this case, we can regard performance as being instructions per second, and we can calculate instructions per second again using a relationship we've previously come across. Instructions per second is cycles per second divided by cycles per instruction. Okay, so for peak performance, it means we can choose our program to get the best possible performance. So since the performance is cycles per second over CPI, to get the best performance, we should choose the smallest CPI and just execute a program with that class of instructions. So if our program consists entirely of class A instructions, we would get the best performance, okay, the best theoretical performance anyway. Okay, so we can take the cycles per second or the clock rate, which is 500 megahertz for M1, and divide it by the CPI-A. The CPI for class A is 1. So for M1, the peak performance is 500 times 10 to the 6. And for M2, it's similar. Again, we can take the cycles per second or the clock rate, 750 megahertz for M2. Again, we choose the instruction class with the smallest CPI. It could either be A or B, it doesn't really matter, they both have a CPI of 2. So in this case, we divide 750 times 10 to the 6 by 2, and we get 375 times 10 to the 6. Okay, so far? And then we're asked a question, assume that the instructions that have executed are divided equally amongst the 4 classes. How much faster is M2 than M1? So again, we're using our same relationship. The performance is instructions per second, which you can calculate as cycles per second over CPI. But now, instead of choosing the smallest CPI, we have to take the CPI, the average CPI, with the instructions divided equally amongst the different classes. So for M1, we can calculate the average CPI. The instructions are divided equally, so we have 25 for 1 quarter of instructions with CPI 1, 1 quarter with CPI 2, 1 quarter with CPI 3, 1 quarter with CPI 4. So we can calculate the average CPI. Okay, so that comes out as 2.5. So therefore the performance for M1 is the cycles per second or clock rate divided by the average CPI, which is 200 times 10 to the 6. Can anybody tell me what it will be for M2? Or how much better is M2 than M1? Anybody worked it out?
Why is it 0.25? Why is it 0.25?
0.2.
Okay, so we can do the same thing for M2. Again, the instructions are divided equally, but A has a CPI of 2, B has a CPI of 2, C and D have a CPI of 4. So again, we can calculate the average CPI, which comes out to be 3, and then we can take the clock rate, or 750 megahertz, divide by the CPI, which is 3, and get 250 times 10 to the 6. So in that case then, M2 is faster by 250 times 10 to the 6 divided by 2, 100 times 10 to the 6, or is faster by 1.25 times. Okay, any questions on that? Okay, the last question is fairly easy, so let's just go quickly through the last question. So we can make an enhancement to the machine which improves the execution time by a factor of 10. So this machine can execute in normal mode where we don't use the enhancement, and you can execute in the enhanced mode and we improve the performance by a factor of 10. Or improve the execution time by a factor of 10. And we're told that the enhanced mode is used for 50% of the time. So first of all, we're asked to calculate the speed up. So the speed up is the old time divided by the new time. So again, we don't know the execution time, but let's just assume that the execution time is A. It doesn't really matter. And then 50% of time A is spent in normal mode, 50% of A is spent in enhanced mode. So if we didn't use the enhancement, the 50% in normal mode would still take a time 50% times A. And if we didn't use the enhancement, 50% in enhanced mode would take 10 times longer. So it would take 50% times A times 10, or altogether we have 0.5A and 5A, so it's 5.5A. Okay, so the old time is 5.5A. So the speed up is the old time divided by the new time. Okay, so the old time is 5.5A, the new time is A, so the speed is 5.5. And then finally, we've asked what percentage of the old time has been converted. So again, let's assume that the fraction y of the old time has been converted, and then we can put that into our equations. So we know the old time is 5.5A, so the fraction y has been converted. After conversion, it goes 10 times faster, so the old time for the enhanced part is y times 5.5 times A. That now goes 10 times faster and takes up 50% of A. So we can solve that equation. So y is 5 divided by 5.5, or 90.9%. Okay? Okay, so I think we'll have to stop there as we've run out of time. What happens with the attendance sheet? So for next time, please look at the questions before the tutorial and try to have a go solving them before the tutorial, and then you'll get more out of the tutorial if you've already had a go at the questions yourself. Okay, thank you.
Last question 3. Just depend on the body.